At the end of the gas laws chapter, everyone's usually feeling pretty good when you are given, okay, this is a Boyle's law problem. This is a Charles law, or this is an ideal gas law. But what about when on the test, the quiz, the assessment, you get them all mixed together? How do I know which gas law equation to use? Well, you do that by doing the same thing I've been teaching you from the beginning. Write down your givens, write down your unknowns. If you have two volumes, two pressures, then yeah, you know which equation it is. You would just compare them to the equations list. You have to choose the gas law that fits best. If they say a variable is constant, you don't have to worry about it. But you will have to make sure that you change your units to what you need, especially if we use the R value, liters per atmospheres, mole Kelvin. I wrote it backwards. Whoops. Okay, so the R for ideal gas law is liter atmospheres per mole Kelvin. We always need to make sure our temperatures are in Kelvin. So let's take a look at a couple of examples. All right, so on this slide here, you will see all of the gas laws that we had. We first did Boyle's law, which is pressure, volume, inversely proportional. One goes up, one goes down. Then we did Charles' law, which is a directly proportional relationship between volume and temperature. That's why they're divided. Or you could have multiplied them out in the cross-multiplied version to get V1T2 equals V2T1. Third, we saw Gay-Lussac's law, which sees a directly proportional nature between our pressure and our temperature. This is the cross-multiplied version. We combined all three of those laws into the combined gas law, P1V1 over T1 equals P2V2 over T2, or if you cross-multiplied it, P1V1 T2 equals P2V2 T1. And then we substituted one side into what we see ideally and introduced the N variable for ideal gas law constant. And we saw some Dalton's law of partial pressures, which we see in our eudiometer lab, and collecting our gases over water, where we have a total pressure is equal to the sum of its parts. So if you're collecting a gas over water vapor, you have to account for the water vapor in the pressure that you collected at. And then lastly, we have our Graham's law of effusion, where we compare the rate of gas A to the rate of gas B by looking at the square root of the molar mass of B compared to the square root of the molar mass of A. And then just some extra little things to remember. Our Kelvin temperature is our Celsius temperature plus 273, and our pressure unit conversions are with atmospheres, torrs, millimeters of mercury, and kPa. So we'll be taking a look at this slide again when we try to figure out what kind of gas law we need. So this is what we're going to do. Okay, we're going to take a look at a gas law, at a problem, and compare it to that page we just looked at and see which one we're going to use. So it says helium gas in a balloon at STP, okay, so temperature and a pressure, is heated to 30 Celsius. So if this is a temperature, this is the second temperature. And then it asks what is the new pressure, so P2 is unknown, so this must be P1, of the balloon if the volume remains constant. So I have two temperatures. I have T1 and T2, and I have P1 and P2. And it says my volume is constant, so I don't really need to worry about the volume because it's not directly involved. So if T1 is standard temperature, that's going to be 0 Celsius or 273 Kelvin. Then I have T2 at 30 degrees Celsius, which if I add 273 to that is 303 Kelvin. P1 is atmospheric pressure of 1 atmosphere in our standard condition, and we're looking for P2. So which of our gas laws is going to use two pressures and two temperatures only? You might be thinking about it right off the top of your head. Peruse them. This is P and V, V and T, two P's, two V's. We're going to use Gay-Lussac's law for this one. And that's exactly what you would do. You would identify what temperatures, what pressures, what's constant, what's not, and then use your equation and constant sheet to figure out which one had two pressures and two temperatures. That's our Gay-Lussac's law. So you would plug into P1 over T1 equals P2 over T2, and then you would get your right answer. Okay, so I'm not going to go through solving those. I'm just showing you how to figure out which law you use. Okay, so example number 2. Let's see if we can figure this one out. How many moles of helium, okay, moles is one of our unknown, occupies a volume of 2.50 liters at STP. Again, a temperature and a pressure. So moles is what I'm looking for. The volume is 2.50 liters. I have a temperature at standard temperature of 0 Celsius, which is 273 Kelvin. Pressure is 1 atmosphere. Okay, so I'm not given a lot, but I do have a gas law that this fits. N should be a dead giveaway, okay? So, ooh, why can't I change my colors here? All right, so N, anytime we have moles, we're going to be using the ideal gas law. There's only one volume, one temperature, one pressure. So we have N, we have V, we have T, and we have P. So you're thinking, but Miss Levin, what about R? R is always available to you. That is the gas law constant, 0.821 liters per atmosphere, liter atmospheres per mole Kelvin. So you can go through and see the ideal gas law right here, PV equals nRT, where R is equal to 0.0821 liter atmospheres mole Kelvin. And you would plug in directly to that. So moles is almost always going to be your tell, okay? If you're going to have moles, then it's going to be the ideal gas law. PV equals nRT, where you have volume, temperature, and pressure. Plug in and solve. The other thing that we could use, which I always think is super fun, is to identify that we have a volume at STP and we want to get to moles. Well, if you remember back to our mole roadmap, remember this thing? We had volume up here in liters, and here we had moles, and we went either this way or this way, and then we had mass over here, and our particles over here. So there's always more than one way to solve some of these problems. So if we have 2.50 liters of helium gas, we're at STP, boom, we can just do that. And that would give us how many moles of helium we would have. 2.50 liters divided by 22.4 would give us how many moles of helium we have because we are at STP. So you can use the ideal gas law or you can use the mole roadmap. Gotta love that prior knowledge. Okay, so make sure that you are looking at your chart, your equations and the constants that go in them in order to figure out which one best fits. And those are our gas laws. I hope you concentrate really hard and pass some gas.